For more than a century, we have believed something fundamental about the universe, that nothing can travel faster than the speed of light. Not a particle, not information, not even a signal. This idea became so deeply rooted that it stopped feeling like a theory. It felt like a rule, a final one, the kind of rule the universe does not bend. But what if that belief was slightly incomplete? What if the speed of light was never meant to be a limit on movement itself, but a limit on something else? If you enjoy calm, careful explorations of ideas like this, you might want to like the video and subscribe. It helps the channel continue moving forward. Every time we talk about faster-than-light travel, we imagine breaking the rules. We imagine engines pushing harder than physics allows. We imagine shortcuts that cheat reality. And for a long time, physics agreed with us. Any object with mass accelerated through space will always fall short of light speed. The closer it gets, the more energy it demands. Infinite energy for a finite goal, an impossible bargain. That part has never changed. But physics is precise in a way intuition is not. Einstein did not say that nothing can move faster than light. He said something narrower. He said that nothing can move through space faster than light, and space itself was left out of that restriction. This distinction sounds subtle, almost meaningless, until you realize that space is not a passive stage. It stretches, it bends, it expands. In the early universe, space expanded so rapidly that distant regions moved away from each other faster than light could follow, not by moving through space, but by being carried by space itself. No laws were broken, no equations protested. The universe allowed it. And that realization opened a door, a narrow one, a dangerous one, but a real one. Because if space itself can move faster than light, then the question changes. Not how do we outrun light, but what if we never needed to? What if faster than light travel was never forbidden, only misunderstood? Part 1. The Loophole in Einstein's Universe. In 1994, a physicist named Miguel Alcubierre asked a strange question. Not how to move faster than light, but how to arrive somewhere without ever violating relativity. He took Einstein's equations at face value. No tricks, no shortcuts through fiction, just mathematics. And what he found was unsettling. General relativity does not forbid faster-than-light travel. It forbids acceleration through spacetime, but it says nothing about manipulating spacetime itself. Alcubierre imagined a region of space compressed in front of a spacecraft and expanded behind it, like a wave. The ship would sit still inside a small bubble of flat spacetime. It would not accelerate. It would not locally move faster than light. Instead, space itself would move, carrying the ship along. From the outside, the bubble could cross vast distances faster than any beam of light. From the inside, the crew would feel nothing. No crushing forces, no extreme time dilation, just stillness. The mathematics worked perfectly. No equations exploded, no contradictions appeared. Einstein's theory allowed it. This idea became known as the Alcubierre warp drive. And for a moment, physics found itself staring at something uncomfortable. A solution that was legal, elegant, and seemingly impossible to build. Because the warp bubble required something exotic. Something the universe does not give away easily. Negative energy. Not just small amounts, astronomical quantities. Energy with pressure that pushes outward rather than pulling inward. energy that behaves the opposite of everything we encounter in everyday physics. To put it bluntly, the original Alcubierre drive required more negative energy than existed in the observable universe. The loophole was real, but it was sealed by absurd requirements. For decades, that is where the idea stayed. A beautiful impossibility, mentioned in papers, referenced in science fiction, quietly dismissed by engineers. Faster-than-light travel remained a mathematical curiosity, until something changed. Not the equations, our interpretation of them. Because Alcubierre's solution was never unique, it was just one arrangement of spacetime, and physics allows many. The question became, what if we could shape spacetime differently? What if the bubble did not need to be so extreme? What if the energy requirements were not infinite, just unfamiliar? That question lingered for nearly 30 years, waiting for better tools, better models, and a willingness to look again at an idea everyone thought they already understood. Part 2. Why negative energy isn't science fiction. Negative energy sounds like fantasy, like antimatter once did, like black holes did, like gravitational waves did. For a long time, physicists treated it the same way. A mathematical artifact, a bookkeeping trick, something that appears in equations but not in reality. But nature disagrees. Negative energy is not hypothetical. It already exists, in small, subtle ways. The simplest example is the Casimir effect. Place two uncharged metal plates extremely close together in a vacuum, closer than a human hair divided thousands of times. Nothing should happen. There is no force, no particles, just empty space. Yet, the plates are pulled together, not by attraction, but by absence. Quantum fields cannot fit all wavelengths between the plates. Some vacuum energy states are excluded. The energy density between the plates drops below the surrounding vacuum. That region has less than zero energy relative to its environment. Negative energy. Measured, repeated, real. The problem is scale. The Casimir effect produces negative energy in quantities so small they barely register. Enough to move nanoscopic objects, not enough to bend space-time. But it proves something crucial. The universe allows negative energy. Relativity never banned it. It only restricts how much and for how long it can exist. This matters, because once something is allowed, physics stops asking if and starts asking how. The original Alcubierre model demanded negative energy everywhere around the bubble. A rigid shell, perfect symmetry, extreme curvature. Modern physicists began asking, what if the energy does not have to be uniform? What if the bubble is asymmetric? What if the negative energy is confined to thin layers or pulsed instead of constant? When researchers revisited the equations with modern computational tools, something unexpected happened. The energy requirements began to drop dramatically, orders of magnitude, then more. By the 2010s, new warp metrics appeared. Some reduced the required energy to the mass of Jupiter, still absurd, but no longer cosmic. Others brought it down to the mass of Mount Everest, still impossible, but no longer absurd in principle. Then came a more radical idea. What if the bubble does not fully enclose the ship? What if it is open, like a wake rather than a shell? A distortion behind the craft instead of around it. That change alone removed entire regions of negative energy. The equations remained valid. The spacetime still moved. The ship still rode the wave. And suddenly, the impossible looked negotiable. This is where the conversation changed, not because warp drive became feasible, but because it stopped being ridiculous. Faster-than-light travel moved from science fiction to speculative engineering. Still far, still dangerous, but no longer forbidden. And when physics crosses that line, history suggests something important. Eventually, someone figures out how. Part 3. The moment scientists took this seriously. For a long time, warp drives lived in footnotes. Interesting, mathematically valid, professionally unsafe to pursue. No one wanted to be the physicist known for chasing science fiction. Then something subtle happened. The language changed. Papers stopped asking whether warp drives were possible. They started asking what they would require. That shift matters, because in physics, questions shape careers. One of the first signs came from an unexpected place: NASA. Not in the form of a prototype, not even a budget line, but a quiet program called EagleWorks. Its purpose was simple: explore propulsion concepts that violate no known laws of physics but sit far beyond current technology. Warp metrics were included, not endorsed, not promised, but examined. That alone was new. Then, in 2021, a paper appeared that caught attention for a reason few people noticed at first. It did not claim to build a warp drive. It did not propose exotic materials. It did not invoke unknown physics. Instead, it did something subtler. It demonstrated a space-time configuration that resembled a warp bubble without requiring large-scale negative energy density in the classical sense. The energy conditions were violated, but not catastrophically, not everywhere. The geometry was different. The bubble was not spherical, it was stretched, flattened, directional. This design reduced the exotic energy requirement to levels that were not zero, but finite, measurable, in theory. More importantly, the authors framed the result carefully. They did not say faster than light travel is possible. They said, a class of space-time geometries exists that allows apparent superluminal motion without violating general relativity. That sentence is doing a lot of work, because apparent matters, and without violation matters. From the outside, the motion looks faster than light. From the inside, nothing breaks. Light behaves normally. Causality remains intact. No paradoxes appear. This wasn't hype. It was caution. And physicists noticed, not because it promised travel, but because it removed one of the biggest objections: energy infinity. Once that disappeared, the conversation changed tone. Skepticism remained, but mockery faded. The idea was no longer dismissed. It was bracketed, set aside as not yet. And in theoretical physics, not yet is a powerful phrase. It means the laws do not stop us, only engineering does. And engineering problems have a habit of shrinking over time. But before imagination runs too far ahead, there is something crucial most headlines ignore. Even if a warp drive is possible, it does not behave the way people expect. It does not grant freedom. It imposes new constraints, some of them disturbing. Part 4. The hidden costs of faster-than-light travel. The idea of moving faster than light feels like freedom. Distance erased, isolation defeated, the stars finally within reach. But relativity is precise about one thing: nothing is ever free. A warp drive does not break the speed limit, it bends the road. And bending space-time creates consequences. The first problem is control. In most warp drive solutions, the ship cannot steer once the bubble is formed. From inside the bubble, the front edge is causally disconnected. Light from ahead cannot reach the ship. Information cannot pass forward. The crew cannot see where they are going. They cannot stop suddenly. They cannot react. They are passengers inside a space-time wave they already committed to. This alone changes the narrative. A warp drive is not a car. It is not even a rocket. It is closer to launching a landslide and riding it blind. Then there is the issue of arrival. When a warp bubble collapses, the energy stored in distorted space-time has to go somewhere. Some models predict a release of radiation concentrated in the forward direction. In extreme cases, this could sterilize an entire planetary system. Arriving somewhere safely may require arriving far away, very far. Another concern is horizon formation. Just like black holes, warp bubbles can create horizons, boundaries beyond which signals cannot escape. These horizons trap particles. They amplify quantum effects. Over time, they may accumulate energy until the bubble becomes unstable. In some scenarios, the drive destroys itself. In others, it collapses violently. Faster-than-light travel may not be sustainable, only brief, a jump, not a cruise. And then there is causality, the thing physics protects most fiercely. Even if no law is violated locally, global timelines become fragile. Under certain configurations, warp travel can create closed time-like curves, paths through space-time that loop back on themselves. Not time travel in movies, but mathematical inconsistencies where cause and effect blur. Most physicists believe nature prevents this, either through instability, quantum back reaction, or unknown constraints. But prevention comes at a cost. The more aggressively space-time is bent, the more violently it resists. Warp drives may exist only at the edge of breakdown, balanced precisely between motion and collapse. This leads to an uncomfortable realization. Even if humanity builds a warp drive, it will not make the galaxy small. It will not make travel easy. It will make it strange, dangerous, and rare. Which raises a deeper question. If faster-than-light travel is possible but costly, why don't we see evidence of civilizations using it? Part 5. If warp travel is possible, where is everyone? This question does not come from curiosity. It comes from discomfort. If faster-than-light travel is allowed by physics, if space-time can be shaped, if the barrier is engineering, not law, then the galaxy should not look this quiet. And yet it does. No probes crossing our system, no distortions in nearby space-time, no signatures of artificial warp fields. Nothing. There are only 3 broad possibilities. The first is simple. Warp travel is possible in theory, but unreachable in practice. The energy requirements, even in optimized models, remain far beyond anything a civilization can realistically control. Not because of intelligence, but because of scale. Negative energy may exist, but harvesting it in usable quantities could require conditions as extreme as the early universe. If so, warp drives are allowed in the same way stellar engineering is allowed. Technically possible, practically irrelevant. The second possibility is more unsettling. Warp travel may be possible, but strategically useless. A civilization that masters it does not gain domination, it gains isolation. Each jump risks instability. Each arrival risks destruction. Each journey requires precise planning with no course correction. That kind of travel does not lend itself to exploration or colonization. It favors secrecy, rare missions, long pauses. A civilization using warp technology would not spread like a wave. It would blink, appear briefly, disappear again, leaving little trace. The third possibility cuts deepest. Advanced civilizations may deliberately avoid faster-than-light travel, not out of fear, out of understanding. Because once a species reaches the level of energy control required to manipulate space-time, it may have already solved the problem warp travel tries to address: distance. Virtual environments, local stellar engineering, post-biological existence. If your civilization can reshape reality locally, why cross interstellar voids at all? Why risk causality? Why announce yourself? Warp drives assume a motivation that may not survive advancement. Curiosity does not scale infinitely, neither does expansion. The galaxy may be quiet not because travel is impossible, but because it is unnecessary. And if that is true, then faster-than-light travel is not the climax of progress. It is a transitional idea, something young civilizations imagine before they outgrow distance itself. But that leaves one final question. If warp travel is not a solution, why does it matter if it may never be used at all? Part 6. What faster-than-light travel really changes. When people hear faster than light, they think of movement, of speed, of escape. But the real consequence of warp physics is not where we could go. It is how we understand the universe. For over a century, the speed of light has been treated as a wall, a hard limit, a statement about reality itself. Nothing outruns it, nothing cheats it, nothing bypasses it. Warp metrics do not break that rule. They step around it. They show that the universe is not governed by speed alone, but by geometry. And geometry is flexible. That realization quietly changes everything. It tells us that distance is not absolute, that separation is not just space, but structure, that what feels unreachable may simply be folded away by the shape of space-time. Even if warp drives are never built, this matters, because it reframes limits. It shows that some barriers are not walls, they are interpretations. The same equations that once convinced us interstellar travel was hopeless now suggest something subtler. Not that the universe is closed, but that it is difficult in specific ways. Faster-than-light travel may never become practical. It may remain dangerous, unstable, rare. But the fact that physics allows it at all tells us something profound. The universe is not hostile to intelligence. It is indifferent. It does not design paths for us, but it does not forbid them either. Every civilization, no matter how advanced, faces the same choice: push against the structure of reality or learn how to work within it. Warp drive research is not about reaching other stars. It is about learning how space-time itself can be shaped. And once you understand that, you begin to see the universe differently. Not as a static stage where events unfold, but as a dynamic fabric that can, in principle, be rearranged. That idea alone is already a kind of breakthrough. Not a promise of travel, but a reminder that even the deepest limits we know are still being explored, still being tested, still being questioned. And somewhere between impossibility and inevitability, physics leaves a narrow space for imagination to operate. Not as fantasy, but as patience. As long as we keep asking careful questions, the universe continues to answer, quietly, on its own terms. Faster-than-light travel may never become routine. It may never become safe. It may never become ours. But the moment scientists discovered that space-time itself can be shaped, something irreversible happened. The universe stopped being a rigid arena and became a structure, one that can be questioned, folded, tested. The real question is not whether we will ever ride a warp bubble. What matters is that reality turned out to be more flexible than we once believed. Distance is not sacred. Speed is not absolute. Limits are not always walls. Sometimes they are invitations to look deeper. Thank you for taking this journey through theory, geometry, and the edge of possibility. If this story made you pause, if it shifted how you see the universe even slightly, let me know in the comments. Do you think faster-than-light travel is a path civilizations should follow, or a temptation they eventually outgrow? If this video helped you think, the best way to support the channel is a like. Subscribe if you want to keep exploring where physics meets uncertainty. The universe is not built for our convenience, but it is open to those willing to ask careful questions. See you in the next one.